There are some nice results, number-theoretical results you can show using modular arithmetic. For example, let's first define what we mean by digit sum. So the digit sum, that's if you have a number like 1, 2, 3, 4, 5, then the digit sum is 1 plus 2 plus 3 plus 4 plus 5. So this is 5, 10, 15. So that's just what I mean by digit sum. Then we have a theorem saying that a number is divisible by 3. So 3 divides a number a. If and only if, the digit sum is divisible by 3. Okay, so 3 divides a if and only if 3 divides the digit sum of a. For example, we have that 3 divides, let's take this number here, 571,908. 3 divides this number because if you take the digit sum, of this number, we have that this is equal to 12, 13, 22, 30. And 3 divides 30. So we have that 3 divides 30. That means that 3 must divide the number. So that's using this theorem. Since it divides the digit sum, it divides the number. Another example, let's show that 3 does not divide 1234, for example. And that's because if you take the digit sum, then we have 7, 10. And 3 does not divide 10. So it does not either divide a number, since it doesn't divide its digit sum. So now we want to prove this one. So let's prove this one. And now the point is that we can prove this one using modular arithmetic. So let a be an integer, and it has its digits an minus 1, and so on. So a2, a1, a0. So these are the digits of the number. For example, if you only have 3 digits, look like this. But in general, we have n plus 1 digits here. Then we can write the number like the position base system 10 in the following way. And so on. And that we can write like this, we have seen in a previous lecture. You can, if you want to go back and check, you can check here up in the corner, the I. And what we do now, we want to show that divisibility by 3. So let's work in modular 3. Okay, in modular 3 we have that 10 is congruent with 1, since 10 and 1 are separated by a multiple of 3. Okay, so that means that if we calculate in modular 3, every 10 here we can replace with a 1. So we have that this is congruent. So now we'll use this. We calculate all over here now with modular 3. This is congruent with an times, and here we can replace 10 with 1. 1 raised to the power n. And this is an minus 1. And this is 10, but we can now replace that with 1. And so on. So a2 times 1 squared. a1 times 1 plus a0. We see here that 1 raised to the power or something, that's just 1. So we can forget about these ones here. So we see that we will end up with the digit sum. So we have here the digit sum. So we see that the number itself here, A, it is congruent with the digit sum in modulo 3. So that means that this number, if this number is divisible by 3, then since it's congruent with this digit sum modulo 3, then this digit sum must also be divisible by 3. And if this is not divisible by 3, then neither this is. So those two are divisible or not divisible by 3 at the same time, since they are congruent in modulo 3. Okay, so we have that A is congruent with the digit sum of A in modulo 3. So that proves the theorem, because the theorem said that A is divisible by 3 if and only if the digit sum is divisible by 3. And that's what the contents of this is, the meaning of this is. So it means the same thing. There are also some other nice rules you can show. For example, you can have a theorem like this. So number theory is filled of this nice number theoretic theorems and interesting results. For example, if we have the following theorem, it says that a number A is divisible by 11. That is, 11 divides A. If and only if the numbers alternating digit sum is divisible by 11. So if 11, here I'm just writing the same thing twice because this is a bit shorter way of writing it. If 11 divides the alternating digit sum, so here we have our theorem expressed succinctly, or a little bit longer here. But then we have to ask ourselves, why is it alternating digit sum? Because I haven't defined that yet. The alternating digit sum just means if I have digits of a number. For example, let's say I have 1, 2, 3, 4, 5. Then I start from right. I start with the smallest digit. Then the next one I take minus, so minus 4. Then I take plus. Then I take minus, and then plus. So that's the alternating digit sum. So this is 1 plus 1 plus 1. This is 3. Or if I, for example, would have had 1, 2, 3, 4 instead, it would be 4 minus 3 plus 2 minus 1. 1 plus 1, 2. It could be other numbers. Now it just happens to be 1 here because we are chosen so close digits. But this is the definition of alternating digit sum. So let me take an example of this theorem. We have that 11 divides the following randomly picked number. So 11 divides this number because we have that the alternating sum, which is 8 minus 2 plus 7 minus 0. It's important not to forget the 0 here, plus 9, because otherwise you get it wrong. So this is 6 plus 7, that's 13, 22. And we have that 11 divides 22. And that means, according to the theorem, that it divides the alternating digit sum, then it divides also the number itself. Okay, so we know that 11 divides this number because the digit sum is divisible by 11. Let's take another example. 11 divides 27,060. And that's because we have 0 if you take the alternating digit sum, 0 minus 6 plus 0 minus 7 plus 2. That is minus 13 minus 11. And minus 11 is divisible by 11. So 11 divides the alternating digit sum, so it also divides the number. Taking another example, 11 also divides this number, and that's because if you take the alternating digit sum, so it's 2 minus 4 plus 7 minus 5. This is minus 2, this is plus 2, so this is 0. And 11 divides 0. So this means that it also divides this number. But finally, for example, 11 does not divide 1, 2, 3, 4, 1234. And that's because if you take the digit sum, 4 minus 3, or alternating digit sum, plus 2 minus 1, that's 1 plus 1, that's 2. And 11 does not divide 2. So these are examples of that rule. So let's now prove that theorem. So again, let a be the number and let an minus 1 be its digits. That is, we have a is equal to an 10 to the power n, an minus 1, 10 to the power n minus 1, and so on. Okay, now we want to show divisibility by 11. So let's calculate in modulo 11. Then in modulo 11 we know that 10 is congruent with minus 1. We don't need a parenthesis. So 10 is congruent with minus 1. And why is that? Because 10 minus minus 1, that's 11. And 11 is divisible by 11. So these are separated by a multiple of 11. So that means that if we calculate now in modulo 11, we can exchange all the 10s with minus 1. So we have that here is minus 1 raised to the power n, multiplication. And then we have an minus 1 times minus 1 n power minus 1. And then down to this, here is squared a1 minus 1 plus a0. But if we now look at what's standing here, this is the alternating sum, because here we see at the first, the smallest digit, a0, then the next one is minus, because here is a0, this is minus a1, this is plus a2, since that is equal to 1, plus 1. So we see that we get this alternating sum. And what number this, what sign this has, it depends of course how many digits we have here, but we see that every other here will be plus and minus. So we see here we get an alternating digit sum. So this is the alternating digit sum. So it means that a is congruent with the alternating digit sum of the number a. Okay, so we can write it up here. A is congruent with the alternating digit sum of a in modulo 11. So that means that a and the alternating digit sum are divisible by 11 simultaneously. So if this is divisible by 11, this is also, and if this is not, it's neither, because they're separated with a multiple of 11. And that proves the theorem.